The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, welcome back, everybody. I'm glad to see more faces today. So the feedback looked pretty good, and once again, I encourage you guys to be brutally honest. I believe wholeheartedly in this whole idea of a democratic classroom, and having this feedback process allows to correct and make this an even better learning experience for everybody. So I handed out a couple things. First of all, I handed out, kind of foremost, Chapter 10 from Douglas Hofstadter's newest book, I Am a Strange Loop, and that's called Gödel's Quintessential Strange Loop. And I think I'm okay, and I'm not going to be sued, because as long as it's less than 10% and it's for academic purposes, it should be okay. And considering this is like 15 pages out of a 300-page book, it should be under that. This is supplemental reading. A lot of you raised kind of notions of, like, Gödel numbering does not make sense. And, well, it takes a lot of time to wrap your head around it. I mean, there's a reason why there was one Gödel and why he named it Gödel numbering. It wasn't like it was a trivial idea. Go ahead.
Is Gödel numbering sort of like an isomorphism between logic and number theory?
So the fundamental idea behind Gödel numbering is that you can take the formal patterns in any type of proving procedure, whether it's the MIU system or whether it's proving from Peano's axioms and number theory, and you can code those formal deductions into manipulations of numbers, right? And then once you create this link, you create this isomorphism into numbers, you can then just play around with these large numbers, which then decoded give you back formal statements in the system you were playing with originally.
So maybe like having an equation with like no solutions, almost having like an unprovable thing.
Exactly. So what Latif said is like having an equation with no solutions is like having an unprovable thing. That's actually going to be very close to the essential idea behind Gödel's proof. But if you read Chapter 10, I believe Douglas Hofstadter does, out of this new handout I gave you, does a great job of explaining some of the key ideas behind Gödel's incompleteness theorem. And that's the main one, that systems as powerful enough as number theory are inherently incomplete. So that's something I want to leave you at least 2 weeks to kind of chew on, because eventually you're going to work on to Chapter 9 in GEB, where he does Mumon and Gödel. And there's going to be, that's where he proves or does a version of Gödel's incompleteness theorem in GEB. But it's really not as clear as I think it's done here. So that's just kind of supplemental reading. So now, on to what I started last time, and what should have been the reading assignment for today, was the location of meaning in Chapter 6. I started out with this idea of the rabbit and GABA guy, but I want to kind of scale back a little bit and really bring the question down to something which some of you will intuitively know and some of you won't have any idea, and it's the following sentence. And please, some of you who know Spanish better, correct my spelling. So, nieve es blanca. Who knows what this means? Okay, so everybody raises their hand and says, snow is white. Okay, but for those of you who didn't raise your hand, what does this sentence mean? It means nothing, okay? Why?
Because I can't relate to it.
You can't relate to it. So far we've kind of got the Latif hypothesis, which is that meaning comes from the relationship of this to yourself. And this is an idea we're going to try to explore throughout all of today's lecture, and we're going to co-teach. Karen and I are going to do some excellent things. So suppose you were dropped off in Mexico, and just by hanging out with people you eventually learned Spanish, and you created a dictionary with a set of recursive rules, and you learned that, well, we have certain things like this is equivalent to is, and you understand this in your natural language, and you create this method of of breaking down sentences, strings, into parts, and then going to your dictionary and saying, okay, nieve es, well, I know es is, nieve, I'm not sure what that is, but my dictionary tells me it's snow, and blanca, my dictionary tells me is white. Okay, so suppose you've dropped off in the middle of Mexico, and just by interacting with the people, and you've created this kind of set of recursive rules for first parsing sentences. And I think that's the more languages you try to learn, the first thing you're going to discover is the stumbling block is the ability to actually parse what someone's saying. I know when I was living in Germany this past summer, basically when someone would talk to me, it'd be like, blah, 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 blah. And I'm like, excuse me? Like, and it didn't even sound like there were words individually. It was just a stream of sounds, right? But eventually, by just being immersed in the culture, my brain ran these kind of neural network algorithms that were able to start breaking up those blah, 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 blahs into, you know, Bier es gut, or something like that. And you could then actually start hearing individual things and then trying to deduce the meaning of those individual parts and then plugging them back together into your natural language into what appears to be snow is white. But what does snow is white mean?
Well, maybe the words themselves don't mean anything.
Okay.
Just add the link to them.
Okay, so Latif claims that maybe the words don't themselves mean anything. But what does that mean? So, all right, so then the question is, suppose I wrote on a piece of paper, snow is white, and I packaged it into a bottle. So there's our scroll, and I cork it, and I throw it into the ocean, right? And it drifts up on shore. What would then be the cue? So then suppose it lands in this island. And you see this bottle. Why would you suspect that the bottle meant anything? Why wouldn't you just pick up the bottle and throw it in your bag of trash as you go and trying to clean up your beach?
Seems very well constructed.
So Latif says it seems very well constructed. So what is it about this bottle and scroll and cork configuration that cues you into the idea that there's information, that there's meaning in here? Paper. Okay, so it seems deliberate in some senses. So the idea that, well, it seems hard that accidentally, you know, some paper crept into a bottle, corked itself, and then sent it through the ocean. So Hofstadter kind of, in this past chapter, breaks things down into 3 layers of meaning. He's got what's called a frame message. We've got an outer message. And then we've got an inner message. So Hofstadter would argue that the frame message here is the fact that there's this strange configuration of a bottle, a cork, and a piece of paper that would cue a human being, any kind of reasonably curious human being, and he argues that fundamentally curiosity is a characteristic of human beings, that there's something to be solved here, that there's information here, that this is kind of screaming out to our stick figure on the island of Tombolia, that decode me, figure out what I am. So suppose then we unpack this piece of paper, and he saw this, but he doesn't speak English. How would he then proceed to try to extract a meaning from this?
You can divide it into words.
So Latif argues we could develop it into words. So how would we, first of all, argue that these aren't just meaningless, scraps of paper, just marks? Maybe it's like a Jackson Pollock painting or something, and it's just appears to be a bunch of gibberish. Sandra, or anyone?
I think there are like repeats, like W.
Okay, so Sandra said that there's repetition. There's appears to be, certain things that there's even this like kind of concept of a space, that there should be something that's parsed here. There's separation into parts. Latif.
Maybe then somebody's trying to fool you.
So Latif argues maybe somebody's trying to fool you. It's interesting. One of the questions I have actually in regards to Chapter 6 that I handed out to you, so I asked you guys to Google the Voynich Manuscript. And the Voynich Manuscript, and that's pronounced Voynich, has been the subject of intense interest by cryptologists for a good 100 years or so. All the guys who were working during WW2 to crack the German Enigma code would in their free time try to decrypt the Voynich Manuscript, because it was this very strange medieval text that had this really intricate system of writing, and it had then pictures of all these sort of alien plants and weird things like this that were not at all found anywhere in Europe, but the book was a European book. So people were wondering, what the hell does this mean? And the problem really wasn't solved until just about a year ago, when somebody showed how you could produce almost an exact replicate of the Voynich manuscript using a random generator. And you would just have like a prefix for a word like go, and then you would have then like a midfix, I don't know what it's called, GL, and then like a suffix. And then you would create like a matrix of these things, and you would shift around and just randomly start generating words. And then they would appear to look like natural intelligible words, but they actually meant nothing. So the Voynich manuscript actually contained no real meaning, but it seemed to trick everybody because it had a lot of the same patterns that human language did. There's some other interesting things that that's connected to kind of parsing information, but I don't really have all the time to go into one of these things. Speaking of W's and letters, there's actually something called Zipf's law, which every kind of language or meaningful message appears to obey. And that's if you rank the most common letters, like I believe E and some of the vowels are the most common letters, they follow a power law distribution, which means that the second most common letter is exactly half as apparent as the first one, and then so on. And it follows this very strict mathematical relationship. And they've even run these kind of power law detections on DNA and extracted that it appears to follow the same behavior as our natural languages do. And if you feel like Googling that, that's Zipf's law, Z-I-P-F. But there's a lot of things going on here, and I want to return to the question, well, what does snow is white mean? And in breaking down that question, what does snow mean? When I say snow, what do you think? Think of snow, okay, but what does that mean? Let's avoid circularity.
Think of a picture of snow.
Okay, so Latif thinks of a picture of snow. What happens to Latif is a visual image is prompted in his head, somewhere in kind of his tangled brain here. The visual section of his brain is activated, and he has a visual memory of snow, or the first time that we had a large snow or a blizzard, and the first time you ever saw snow. What about anybody else? What does snow mean to you? So then we've got kind of in some ways, a tactile sense of being cold. So then another part of Latif's brain here lights up when you say snow, and it goes to all the times you've ever felt cold. Maybe just sitting in this room and having the air conditioning up a couple notches too high. You have a feeling like, geez, it's freezing in here, right? And freezing then triggers idea of frozen water, which triggers the idea of snow. But what else? What does snow mean to you? Some of you might see it as, oh, well, this is an opportunity to go, snowboarding or something, right? Sorry, here's my bad recreation of bindings. Or go skiing or something, or it's recreation, it's time, it's winter, it's a break from school. There's a whole really complex conceptual network in everyone's brain with the word snow. Just like if I were to pick apple, and I ask people, when I say apple, completely out of context, what is the first thing you think of?
Pie.
Apple pie, okay. Anyone else? Orchards. Anyone else? Red. Adam and Eve. I'm glad someone said it because I thought I was going to have to. So what then do you associate with the apple and the Adam and Eve? Say it. Okay, so then we've got, wow, holy mackerel. We've already gone from apple to God pretty damn quickly. Maybe I should draw that off of Adam and Eve if we want to make it seem like that was the track we fell. But then what was it that Adam and Eve were being punished for eating the apple? What was it? The tree of knowledge. How did Newton discover gravity? What computer am I using? Mac. Excellent. Or your iPod or whatever. So immediately, if somehow I could look at your brain and kind of take an ongoing, PET scan of what's lighting up as I say the word apple, it would be this extremely complicated explosion of electrical activity in your brain that lights up and tickles every part of this section of your brain that relates to the term apple, right? Now, of course, then when I have a frame of message, like this apple is tasty, right, then you immediately narrow down, well, what is he talking about? Is he eating about just a fresh apple, a red apple, a Granny Smith apple? Maybe he's talking about eating apple pie. So you prune kind of your ongoing neural net, and you stick to this side. So I've noticed that nobody's come and claimed their $1 or $2. And this is, I think, a convenient point to pull out a dialogue we did a long time ago. Does anyone remember the Contra Crosta Punctus? And, just as an apple has multiple meanings, this dialogue, page 75, has a variety of meanings. I needed someone to start reading off the first letter of every sentence that Achilles tortoise says. Sorry. So I think it's H-O, right? So we go.
Oh, right.
Yeah. So go Achilles tortoise.
Oh, sorry. H-O-S-T-A-T-T-E-R.
All right. 1 second. S-C-O-N.
S-C-O-R-A.
S-C-O. Sorry. S-C-O.
S-C-O-R.
S-C-O.
Oh, no, sorry. S-C-O-N-T-R.
N-T-R.
A.
I think I have too many S's here. A. C.
R.
R.
S-T-I. There's an
O S T I P U N C A C R S T I C
A L L Y B A Y A R S S P E L L S J period S period B A C.
Did anybody see this? So, and I should have asked it as a homework assignment, but one of the things that the turtle and tortoise and Achilles says is, starting page of 81, he says, there are many clever ways of hiding things in music, Achilles says, or in poems. Poems used to do very similar things, though it's rather out of style these days. For instance, Lewis Carroll often hid words and names in the first letters or characters of the successive lines in poems he wrote. Poems which conceal messages that way are called acrostics. So we already had kind of a frame and outer message screaming out, saying, I'm talking about me, sillies. Decode me. And it's already from the dialogue, which had its one level of meaning, it then, within itself, pointed upwards to a higher level of meaning, which is this acrostic we just pulled out. But what does the acrostic tell us to do? Sure. And what does that get us? Sorry, acrostically, there shouldn't be a space here, so join that over there. Let's see. Well, if we then look at this as another acrostic, and we take the first letters of each word, what do we get? And then the third, and I think probably the highest level of meaning we can extract out of this is J.S. Bach. So to what extent does contra crosta punctus mean J.S. Bach, right? And there's, I think, a lot of really neat stuff going on when he kind of asks about messages which can talk about themselves and also build themselves, right? And that's basically what we did here, is we had a dialogue which gave us instructions on how to extract meaning from this. And then it in turn gave us another message which told us how to extract meaning from it. And in some ways it's a really inefficient thing to do, because what was, I don't know, it was like a 10-page dialogue. That much was needed in order to extract the inner message, or one of the inner messages here, being J.S. Bach. So that's kind of a poor compression ratio here. It took 10 pages to tell us one name. But I think it's interesting nonetheless. But still, not everybody picked this up. So to what extent does this dialogue mean J.S. Bach? Well, I would argue not to a large extent, right? And fundamentally what I'm going to argue here, and this kind of goes with the Latif hypothesis or conjecture, is that meaning is not inherent. And to expand on this, and this is what Hofstadter calls the jukebox theory of meaning. Meaning is the relationship of things. But what does that mean? What I'm trying to argue here is that Apple, if we wrote Apple on a piece of paper and we shot it out into outer space, and maybe some alien civilization came upon it, that there's not really much inherent meaning in having a few ink blotches on a piece of paper, or in here I have some limestone broken onto a piece of rock, right? To what extent does limestone broken onto a piece of rock mean anything, right? And the only reason we say Apple has meaning is because there's this complex isomorphism between the visual input of Apple when you read it to the electrical activity in your brain, right? Just like, and I don't actually know any Chinese here, but I can try to construct a character, and to what extent does that mean something? And I could have someone sitting in here and say, well, no, that's actually the Chinese symbol for tranquility, right? But how was I ever supposed to know that? How was I supposed to discern this from nonsense? And really, this shows that meaning doesn't lie here or here, but it lies here, and the relationship of things. So the extent to which this means anything is the extent to which it has a direct correlation in the minds of the people using the terms. It's just like when you have these native languages and they die out. They no longer carry meaning, or really they continue to exist in any way, shape, or form, is that you don't have people actively using and kind of interplaying in this complex feedback process of modifying what these things mean. Because also think about how these symbols, how these marks on this limestone have changed in meaning. If we were to rewind 100 years ago, Apple would definitely not mean laptop, right? And I don't know if the myth involving Newton and his discovery of gravity, which is a myth by the way, existed 100 years ago, but let's suppose it did. But let's rewind 500 years ago. Then this would absolutely have no connection with Apple. And we would have this would be the supported neural network of what this string meant. So fundamentally, I'm arguing here that this only means as much as the stuff it causes here. But this brings kind of a reverse question. I mean, with an isomorphism, you go two directions, right? So suppose instead, and this is really what a lot of neuroscientists would love to do, I just had a camera running of all the activity going on in your brain, and I wanted to reveal your thoughts. To what extent could I say, firing in sector B 8615G means Apple, right? To what extent can I say that, right? And this is actually going to bring forth a really important question, which will be the exploration of the rest of today's lecture, is to what extent does physical activity have meaning? How do we distinguish between random physical things and pattern physical things, right? What was it when Galileo was bored in church and he looked at the pendulum rocking back and forth, and he would use his heartbeats to keep track of the period of the swings, and he noticed that it was always the same. And it didn't even have to do with how big this mass was here, but it seemed completely based on the length. Now, in some ways, what is the meaning of a swinging pendulum, right? And if I wanted to describe a pendulum to you, I could do a variety of things. Just like I could ask, well, what does the firing in your brain mean? Ideally, in the future, we'll be able to say, well, that particular sequence of firings in your brain meant you were thinking about an apple. But what happened, fortunately, a couple hundred years ago, is that somebody was looking at this, and they realized that they could do better. Instead of just filming the phenomenon, instead of just saying, okay, well, what happens when a pendulum swings? They're like, well, the best level of description we can do is, a streaming 256K video webcam of a pendulum, right? I mean, that's a really bad compression, right, to encode the information. Keyword, information. Fundamentally, what I'm going to argue, we're pulling this down to, is to what extent is there information in here? And the study of theory of meaning and information theory is going to be our mathematical and rigorous approach to what the theory of meaning is. So how much information is in this, right? And what it took was that somebody eventually realized, well, I can describe this complex motion actually rather simply. Well, if I looked at the angle theta that it makes, I could say, and I apologize to you who haven't had calculus, but when I have a dot above the symbol, I want to see how quickly it changes with time. So if this were just a single dot, I would mean what's the kind of just change in time of the angle theta. But if I had two dots, I'm asking what's the change in time of the change in time of the angle theta. And you can think of this as acceleration, whereas a single dot would correspond to velocity. I can actually write down the equation of motion of a pendulum as such. Theta double dot plus, and this is just a constant, sine theta equals 0. And then if any of you, as you eventually will learn, is that this is too hard to solve as an equation, but instead we express it in a linear form. And don't worry if you don't know what any of these terms mean. Or we approximate sine theta, which some of you have seen in pre-calculus, or even geometry, as just theta. Around 0, we can approximate sine theta, passing to the origin, sorry, as just the linear function of theta. But the point is, don't worry about the mathematics here. I could be talking about any system, and what we'll show you today is that what the project of physics is, and what the project of all of science is it's reverse engineering, right? All of what Hofstadter has been talking about in chapter 6 has been going one direction. You start with a string, and you ask, well, what does it mean, right? And my answer was that, well, what apple means is it means the activity in your brain. And then we could say that, well, it actually refers to the physical apple somewhere out there in the universe, but that becomes a difficult problem. But then what about going the reverse way? To what extent does activity in your brain mean this? Is the same question, which Hofstadter doesn't talk about, as to what extent does the motion of a pendulum, just kind of rocking back and forth. Let's see, do I have anything? There you go. To what extent is the meaning of this motion encoded in these marks on a piece of paper? And this is actually, in some ways, a much harder question, is how do we take the output and code it into the input? And what we're going to be doing today is playing with some active computer simulations and showing to what extent does the output we see on the screen, can we figure out just from that what was the underlying mechanism? And really what all of science and physics has been about is showing that the complicated motions of the entire universe can be explained very shortly using symbols like this. And this is going to get to an idea that we're going to call algorithmic complexity, right? What's beautiful about the pendulum is that it doesn't require a streaming feed all the time to describe its motion. I can write it down in one line of mathematics and give you the complete time evolution of this system. And even with the initial conditions of how fast was I swinging it initially and from what place, I can get to this whirling phenomenon. I can get all sorts of incredibly complex behavior out of just these marks on a blackboard. And then similarly, when some of you were here 2 lectures ago and you looked at the Mandelbrot set, an extremely complex fractal, what if somebody had handed you that and said, tell me what equation produces this? For the most part, you couldn't have done it. What,
It
Latif?
seems like an equation sort of hiding the information. And because you just look at the equation, but in your head, all this stuff you're talking about, but the physical thing is actually inside your head, but it's being sort of connected with the symbols. So you just adding stuff to the symbols.
Okay, so Latif said, well, isn't all of mathematics just really hiding the information? So, and what I'm going to kind of do, and correct me if my interpretation of what you said is wrong, is that really all we're doing is we're taking our mental process, our visual input, and we're abstracting away the details. We're creating an abstraction barrier between that and this. But I would argue, to an extent, no, right? Although fundamentally, this sentence is only meaningful to mathematicians, right? And thus the models they have in their brain. But this actually reveals a very simple relationship of, so what happens when we talk sine theta, how would you parse that? Well, you might draw a circle and then say, okay, if I had a triangle here, I would say that sine theta is opposite over the hypotenuse, right? And the fact that this has a relationship with that involves some serious thinking. But yes, you are masking some of the details. But if you wanted this to run on a computer, it would be much more efficient to just code this up in a programming language than to take a film, right?
You can do that, but when you unwrap to find out what those symbols actually stand for, it turns out that you're not really abstracting it too much. You're just making these symbols just stand for the thing itself.
Okay, so Latif's saying that's fundamentally still what we're doing is we're saying that we're letting the symbols stand for the thing itself. But I'm still going to argue against you, right? And the reason for that is that there's something unifying behind looking at the arm swinging in a clock and what I'm doing with this cable. And then as you'll start to study more, and as we'll show today, throwing a rock in a puddle, and then just getting this entire wide class of oscillatory phenomenon. What is it like to do this, right? And we're going to see it everywhere, even when, and you can really observe this when you're driving. And then we're going to get into wave equations. The idea of when you're driving down a highway and you hit a kind of a backed up section of traffic, what's happening is that the guys in the front stopped, and that forced you to stop, and that forced the car behind you to stop, and you propagated a wave backwards. But still, we can describe this entire large set of a seemingly unrelated physical phenomenon. We're not talking about this single clock. We're not talking about this single pendulum. We're not talking about this single cable. We're talking about a whole variety of phenomenon and just writing down this equation. And I think that's a really neat thing. But this is a phenomenally hard thing to do. It's hard to see all of these classes of phenomenon. It's hard to see me throw this piece of chalk in the air and extract the equation which describes it, right? So what we're going to spend the rest of today talking about is not how do we go from apple, or how do we go from the equation to figuring out, well, what does it mean, right? And it's like the same question of, does x squared, does the equation y equals x squared, does that really mean the graph of x squared, right? And you're going to see that, no, it doesn't always. It can mean a whole variety of things. I don't even have to graph it. I could be talking about a different domain and all sorts of different phenomenon. But it's going to be the relationship of these different ideas that we're going to be talking about. And we've got some great things to show for you. And for the most part, I'm going to be handing this. Sorry, yes, Latif.
Isn't it when you see all these similarities between different structures, and we making stuff up?
So are we making stuff up?
Yeah.
Yes, we are making stuff up because we're only modeling things here, right? Like if you actually then measured, you know, does the rate of change of the angle of this cable always equal minus the sine of the angle? And for this system, obviously, no, right? Because, I mean, look, it's bending, right? And it's got all sorts of weird elastic properties. It's actually, the rod's not stiff. It is actually flexing about and doing all sorts of crazy things. And, you know, this isn't a massless rod here with just a big ball on the end. This thing's got almost as much mass as the end. So no, but the fact that we can model most of the behavior, most of the salient features of the phenomenon in a rather simple way is one of the remarkable things about science and about mathematics. So just to kind of convince you that complexity can come out of simplicity, you might say, okay, well, doing this isn't really that complex. I mean, I probably could have figured out a simple way to describe it. Go ahead.
Does that show something about the universe or something about us? Because you see, maybe the universe is doing the same thing, just more complicated and just showing how you can do it like.
Okay. So Latif says maybe the universe is doing something different and we're just showing how it can be done simpler. That's a good question. But the problem is that the most we can do, the way that we fundamentally think as humans, since we're such simple creatures and we're not the universe, well, we're part of it, is that we have to be able to simplify our phenomenon in ways like this. And if you ever end up reading a book by Seth Lloyd called Programming the Universe, you'll say that the universe itself is a quantum computer carrying out quantum operations all the time. And maybe somewhere in there, at the beginning of the universe, there was a monkey typing away instructions into the quantum computer that is the universe that said, okay, well, we're going to let force always equal mass times acceleration, for those of you who have done physics. And we're also going to let this, and we're going to, and this was all hard-coded in there. But the issue is we don't know that. We don't know what happened exactly at the beginning of the universe. We don't know how exactly the universe operates. There's still mysteries out there. And the fact that we can go from throwing this piece of chalk to understanding what's the law which governs that is really a remarkable achievement of humankind. But I want to really hammer home this idea that complex phenomenon have a very simple underlying feature. And this is going to relate to some different ideas of information theory, which I might periodically pop in and invade on Curran's time here. But for the most part, he's going to take over the show now. But should we take a quick break?
Yeah, let's take a break.
All right, so let's come back in probably 5 minutes and refresh ourselves. So, and then Curran will take over. All right.
Okay, so I'm going to start talking. So this is the Sierpinski triangle, which I talked about last time. And there are a lot of different ways to get to this shape. So he's talking about how do you go from seeing this shape to understanding the process of how to do it. It's not like an easy thing. This is what's sort of unique to humans. We can step back and say, like, okay, what's going on here? What kind of more generalized process might lead to this thing? So I'm going to talk about a bunch of different systems, Lindenmayer systems and cellular automata, and a bunch of examples of each. So first of all, I'll just do an example of a Lindenmayer system. A Lindenmayer system is when you start with a string. A string is just a list of symbols, like characters. And you apply these rewrite rules, and you have this grammar. So each one of the symbols goes to some other set of symbols when you rewrite it. So I'll just do an example. We start with F, and we have these rules. F goes to, well, this means it's a string when I put it in quotes. F goes to F. So whenever we have this symbol F, we replace it with F plus F minus minus F plus. And like, does this mean anything to you guys? Probably not. So let's just go through it. And so F, when we apply the rule for the first time, what we get is this. We get F plus F minus minus F plus. So here's when we really get to the recursive nature of Lindenmayer systems. We feed this string back into the rule. And so for each F here, we replace it with that. So this F, the first F becomes F plus F minus minus F plus. So that's what this first F becomes. Then we add plus the second F, and we do that whole string of stuff again, minus, and then another repetition of that, and then plus. And we just keep doing this. And now let's recall the Koch curve from last time. What we do is, the first thing, we have this, just a line. And we apply this rule that says we make this little notch in it. So we get to this. And then we apply that same rule to each one of these things. Right? So what does this mean? Does anybody have any idea what this means? These symbols. So the meaning comes out of the isomorphism, like he said. How do you interpret them? So F, in this case, F stands for going forward. What? Yeah, this and this are actually the same thing. This is the power of Lindenmayer systems. So F stands for going forward, and plus stands for changing the angle by 60 degrees, and minus stands for changing the angle by minus 60 degrees. So first we do the first, I'll just use this board. The first F is just this. This is F. And this is the second one. So F forward plus 60 degrees. F plus 60 degrees. F minus 60 degrees, minus 60 degrees again. F plus 60 degrees. F. Sorry, there should be an F on the end. They're all wrong. But this is what you get. You can think of, the way this is taught is think of a turtle. And a turtle has an X, Y, and a theta, a position and a rotation. So each symbol is interpreted as having some sort of effect on this turtle. So I wrote a program that does exactly this. So let's look at that. The Koch Lindenmayer system. So I'll just quickly go over the code. So we have turtle X, turtle Y, turtle theta. This is the important thing. This is where the turtle starts. So, and we start with this string F. And so this is F, the first string. And for int I less than depth, I plus plus. This just means do this certain thing depth times. And depth is a variable. So when I click on the screen, depth increases by 1. string, which is f, equals string, like what the string is now, replace everything in that string by the specific thing. Replace f by f plus f minus minus f plus f. And then we interpret it. We give the symbol's meaning by this isomorphism, how we interpret it. So for each character in the string, if the character is f, then what we do is we store the previous values and we move forward. And cosine of sine is just how we interpret the angle, go forward, times the increment, which is the length that we go forward by. And we add a new line with those x and y values. So this is what f means. And then plus, what it means is just turn the turtle a little bit. Turn the turtle's angle by pi over 3. And likewise with minus. Subtract from the turtle's angle pi over 3. So we can run this and see what it looks like. And I added some more things like mouse listening. So first of all, and it's printing out the strings. So this right here, if you can see it, says f. So I'm going to click, and it does that, just the rule that we were talking about. And now the string says f plus f minus minus f plus f. And when it's interpreted, it gives you this picture. So if we click it again, apply the rule, feed it through, we get this. And it prints the string here. So this is the next string. And then we do it again, and the string gets longer. So we can do it again and again and again, and we get the Koch curve, which is this strange curve that has, infinite length, which is pretty wild. Any questions so far? So a Lindenmayer system is very general. Yeah.
Can you go back to the picture?
Do the picture again? Sure. So.
What if you see it backwards? Is it going to be the same?
What?
Like flip the picture over and see it that way.
If you flip the picture over?
It's like you have a certain shape. What if you take the other shape? Like you have the boundaries of the shape. What if you take the other
You want to come up in motion and show what you mean? If you were to view this curve as starting from here and going to here,
would it be the same rule?
and it's upside down, it's the exact same thing. Yeah. That's why it's a fractal. There are copies of itself inside of itself, nested infinitely. That's what it means to be fractal. So for example, this whole thing is this right here. This thing is the same as the whole thing. And likewise, a smaller version of what you were saying. If we flip this upside down to here, it's the same thing. Yeah. So yes. Isn't that cool? So here's another Lindenmayer system, which is a bit more confusing, I think. But it's the same idea. It's a rewrite system, Lindenmayer system. So we start with the string A. And then the rule for grammar is A becomes B minus A plus B, and B becomes A plus B minus A. And the string becomes that. And what these things mean is if it's A or B, go forward. And plus, go turn the turtle one way, and minus turn the turtle the other way. And so what we get here, I'll run this and we can see what it looks like. So first we start with this. This is just a line. And we apply the iteration. This is twice, actually, because if you iterate it once, it goes like upside down and off the screen, so I just didn't do it. So this is after 2 iterations. So think carefully about this shape. Yeah. So I'll just iterate it again. And we'll notice that from each one of these lines, this shape is going to grow again. Only in alternating directions. So the original line was here, here, here. So here it grows this way. Here it grows that way. Here it's that way. It goes that way. There it goes up.
It's like it's interlocked within itself.
Yeah, it is like it's interlocked within itself. So I'll iterate it once more. And from each one of these little lines is going to stem one of those shapes again. And it's approaching the Sierpinski triangle. So we do it again. Come on, do it again. There. So it's just a bunch of little squiggly lines, but it's becoming the Sierpinski triangle. So, yeah.
Did you say F string, or what string did you use?
For this?
Yeah.
So this string is not F, but it begins with A. It starts with A here, and it applies these rules to it. So this is the printout of what the string is. So first it's A. After 2 iterations, it becomes this. And then every A in this second string, every A here is going to be replaced by this thing. And that's what we get with this one. It just goes off. So, but it's a similar concept. So this is the string. And likewise with the tree. I had a tree example last time. And we can make a Lindenmayer system for a tree. And the string is FBR. So if we look right here, the string is FBR. And the rule is every B becomes this. So we can really think about this and give these things meaning by interpreting them. So F means go forward. B means there's a bud on the end of the branch. And R means reverse. So let's think of building a tree. We're going forward. So F, and on the top there's a B, bud, and then R, reverse. And the rule is each B, right here, each B becomes this. And we'll see what this is, what this means. Each B becomes minus FBR plus FBR minus. So each B, each bud, becomes minus FBR plus FBR minus. Yeah. So let's run this and see how it looks. Anybody have questions so far? Yeah.
So why are all your strings palindromes?
Why are all the strings palindromes? Wow. They're palindromes because each side of the tree is exactly the same. That's why. And by the way, if you don't know what a palindrome is, it means it's the same forward and backwards. Is that what it is? Right? And it makes sense because the tree is the same if you flip it around. So I'll run it. So the first thing is FBR, forward, bud, reverse. Do it again, and it's this tree. There we have it. So look at this picture, and I'm going to show you this other program that I explained in my last lecture with this recursive function that says tree, grow tree with the smaller size. And I'll run this. And lo and behold, what we get is the same thing. This is the Lindenmayer system. And this is the recursive function. They're exactly the same. So what does this mean? Like there's something deeper sort of about fractals. Like you can approach them from different angles and get the same thing. I'm just fascinated by it. So I'm going to move on to cellular automata now. Any questions on Lindenmayer systems? So cellular automata, yeah.
So if you get the same thing, does Voynich Manuscript systems equal samples, they have an isomorphism relationship with fractals?
Yeah. So you're saying your question is like,
They approach different ways and they equal the same thing. So in those two different approaches, do they equal each other?
in some way, yes. So what she asked is, so you have two different approaches, and if they approach the same thing, are they in fact the same thing? More or less, is your question?
So is the idea that really we have two different descriptions for the same phenomenon.
Yeah.
So to what extent are those descriptions the same?
Huh. So right, I mean, it's sort of mind-boggling. We have two different descriptions for the same thing. So to what extent are the descriptions the same? I mean, they're definitely different, but they describe the same thing. So the thing that they're describing is the same, but they themselves are different. I mean, it's hard to really say. Yeah.
Is it sort of like describing like an outside object maybe in visual terms, maybe like verbal terms?
Say again?
Like describing something as visual, other than like audio or something.
Describing
words about it, or like
okay. So he's sort of making the analogy to describing something in reality using words or using pictures or using sound or using text. So yeah, what you're getting at in all these different descriptions is the same fundamental thing. This is the inner message, right? That Justin was talking about earlier. You have the frame message, the message, and the inner message. The inner message is the real meaning, the thing itself.
But could also like the physical thing be like another way of describing something that's more abstract? Maybe like physical reality itself is like describing like it's like a description of something more abstract than
Oh man. So he said, so maybe physical reality itself is just a description of something else more fun.
Yeah, like mathematics is also another description.
Mathematics is also another description of thing. Maybe mathematics itself is the thing being described by the physical universe. I mean,
Seems like we have a Platonist on our hands.
we have a Platonist on our hands. Yeah, so it's sort of like asking the question, so all of these different descriptions of fractals all lead to fractals. What does it mean? Is the fractal itself describing something deeper? I mean, I don't know. We sort of get that sense, but it's like, it's so elusive. Yeah.
Deeper into the fractal, since it's recursive itself? Like, is there, like,
Can you go deeper into the fractal?
like a definite...
There's no, it's scale free. Yeah, it's scale free.
Yeah.
The fractal itself is...
Contained in itself.
Yeah. I mean, yeah, you can go into the fractal infinitely. Yeah. But like, what is it? What are the implications of that? Like, I don't know. It's just, yeah. Where does it lead to? It leads to more of itself. I guess it's recursive. You know, there's no end. Yeah.
But the universe is almost affecting like in a more abstract sense because it talks about itself. It has inside of itself like descriptions of itself, mathematical descriptions of itself. And a lot of times it just repeats itself out of these space as well. So we also function in more abstract sense.
Could the universe be a fractal in a more abstract sense? Yes.
That just references itself over and over.
Yeah, I just have to put in there because before you had like kind of a quantum mechanical version of the atom. What we used to say is like, well, here's the nucleus, and here are the electrons, all right? And of course, I could have said, instead of nucleus, here's the sun, and here are planets. So in this sense, now, once again, I mean, this model isn't right, but what we used to have, this kind of self-similarity across scales, is that, you know, if we zoomed in far enough from our solar system and went from the solar system and just kind of kept just telescoping in and in and in and in visually until we got to a length scale on the level of atoms, I could replace this, and it would look exactly the same, and I would say, well, this is the nucleus, and here are electrons. Of course, this isn't exactly right, but what's interesting is that a lot of physical phenomenon, I mean, and this is a very kind of deep experiment, is that, and I know Curran talked about this a little bit, but if you take a mountain and you look at the shape of a mountain, that's kind of this crinkled, fractally thing, and then you take a piece of paper and you crumble it up and then unfold it, the geomorphology of a paper is almost exactly the same as a mountain and the landscape around it. So in some senses, there's a self-similarity in laws, in conceptual laws, between the forces that govern the shaping of mountains and valleys and rivers and the forces behind me crumbling up this piece of paper.
And also, in biology, it's so inspiring. In biology, you see these patterns at different levels, on different scales, and they're all the same. They all share something. So I mean, biology, like yourself, like your own body, is definitely a fractal in some sense. Not infinitely, but there's all these, yeah.
Could it be like the thing itself or the way to describe the thing?
Ooh. So Latif said, could it be the thing itself or the way that we describe the thing?
Yeah.
So then that fundamentally boils down into, which do you think's realer? The pendulum or the equation describing the pendulum?
It's like a chicken and egg example.
Okay.
Like
So Sandra says it's the chicken and the egg example. Yeah.
So speaking of biology and life, life is complicated, right? Life is complex. Societies just evolve and people do things, and like you can't really predict what's going to happen, and you have all this complex behavior. But and in society, it sort of arises from complex rules of interaction between people. But with computers and cellular automata particularly, what we can do is very, very loosely model life, and we get this. And it's similar to actual society in that, like, it's very complex behavior, and we can't tell by looking at it how it's going to end and what's going to end up. Maybe small things could balloon into, huge influential events, like people, like one person, influences the whole future. Like, it's fascinating. So what I'm going to do is talk about these rules and what this program is, how it works. So this is Conway's Game of Life. It's really cool. So we have this grid of boxes. And each box is termed a cell, cellular automata. And that's automata because it evolves, it keeps going based on simple rules autonomously. Like, it does it by itself. So we have this huge grid, and you can think of each cell here as though it were its own little organism, just sort of going through life. So let's consider this one. If we are this cell, like a cell is a place for an organism to exist or not exist. So there are some very simple rules. You haven't written down? It'd be good to just have a piece of paper that said them. Sure. Oh. Right. So a cell is either filled in or it's not filled in. So if we are alive, say we are this cell right here. If we're alive and there's only one cell around us, we die of loneliness. And so this cell would die. If there are two cells, it's okay. It's a healthy sort of environment. Like, those are our parents maybe, and we live. We're this cell. If there are three, maybe it's our parents and a brother or something. We live. But if there are four, and these numbers I'm talking about is the total number of living cells in our neighborhood. So these surrounding 8 cells is the neighborhood of this particular cell. So if there are 4 living cells in the neighborhood of this one, then it dies of overpopulation, of suffocation. 4 or more. If there are more than 4, then the cell dies. And if the cell, what?
Yeah, good.
If the cell is not alive, then if there are 3 in its neighborhood, then it comes alive. So if there are 3 cells around it that are alive, then they birth a child or something. So this is the entire rule set. These very few number of rules that makes this thing happen. So it starts off with just randomly filled in cells. Oh no, what have I done? It starts off with just randomly filled in cells. And let's just look at the code quickly. Cellular automata. So neighboring cells is get cell x, y plus 1. And we go through this list of things. We basically get all the cells in our surrounding neighborhood and put them into a list. This notation means array. This is like a list of cells. A cell is an object, which I made, which has a property of either being alive or dead, basically. And it's drawn as a square. And so if my value is 1, my being the cell that we're considering at the moment, and mind you, this is inside of a loop. Note this double for loop for each x and for each y. So the stuff inside of these double for loops is going to be executed once for every cell. So let's look on the inside. So my is the cell at xy. If my value is 1, meaning that I'm white, I'm alive, there's something living in this cell. If there are less than 2, then I die of loneliness. If there are more than 3, then die of overpopulation or suffocation. So this can be encoded as if this neighborhood sum, which we calculated a few lines ago, just added up for each cell in neighboring cells. Neighborhood sum is you add that cell's value. So for example, with this cell, neighborhood sum would be 3, right? The number of living cells around it. If my value is 1, then if the neighborhood sum is 2 or 3, so if there are 2 things around me or 3, then my next value, the value that I will be in the future, is going to be 1. I'm going to stay alive. So otherwise, I'm going to die. Value is 0. My next value is 0. So else if my value is 0, this means if the cell is originally dead, if the cell is originally black, there's nothing there. In that case, then, if the neighborhood sum is exactly 3, then my next value is 1. Otherwise, I stay dead. So if there are 3 people around me, then I'm going to be born into this cell. That's basically it. And we calculate the colors and whatnot. But that's the essential piece of the program. And when we run it, this is what we get. Conway's Game of Life. Any questions? Yeah.
Does it ever repeat itself?
Does it ever repeat itself? Well, we'll see. Now it's repeating itself every 2 frames.
So it's actually hit a steady state now.
So you can go on forever, it will never change.
At this point, yeah, it's in a periodic cycle, so it's never going to change.
So I can
But
put in random data to make it change.
so let's see. Does my mouse click work? I don't remember. No, it doesn't work. But I mean, it depends on the initial conditions, right? Let's do it. Let's run it again. Oops. If we run it again, it might never do that because the initial conditions are random. Think of this as a computer program. This is the halting problem. of computer science, Alan Turing's halting problem. So that basically said that, and this is in the handout, I believe. Is it, Justin? Maybe not. Oh, sorry. But Alan Turing's halting problem says that if you have a given computer program, there is no computer program that you can write that will analyze that program and tell you whether or not it will stop. So stopping, halting, coming to an end or coming to a stable point is unpredictable. It's impossible to predict, given a set of inputs, whether or not the system will ever come to a stable point. So the configuration of cells initially is actually a computer program that's going to be set in motion when we start the simulation and start applying these rules.
So we can get like the whole Turing machine thing just by moving these on themselves, right? They're almost like doing the same thing.
So you can,
like a Turing machine. And
a Turing machine, right? So yes, applying these rules can be reduced to a Turing machine. Yeah.
And the Turing machine can also be reduced to that.
What? A Turing machine is like the lowest level of existence of a computer program. Like it's.
Right, but I think it's equivalent. I'm not sure if I think Game of Life is, but I know some other cellular automaton rules are universal Turing machines, right? So you can either think of it as a strip of paper, which is just doing very simple computations back and forth, or you could also do your computation on the level of squares in cellular automaton like this, and what that means to be a universal Turing machine is that you can fundamentally reproduce the basic logical operations of and, not, and copy. And from that, you get essentially all of mathematics and all of anything you'd want.
How about like Gödel's incompleteness theorem? Can you get all of mathematics from just logic?
Okay, so that's kind of a... So the touchy issue there is, can you derive all true statements recursively from a set of axioms? No. Gödel's incompleteness theorem tells us this. And that's why mathematicians will never go out of a job, right? Fundamentally, there's always new truths out there that aren't reachable from your set of axioms. So you kind of have to go out there and meta-think and then discover it, right, from a higher level outside of just a recursive operations acting on axioms. But interestingly enough, Gödel's incompleteness theorem and the halting problem are really fundamentally kind of the same thing. Because the way you prove the halting problem is you feed the program, which is supposed to decide whether or not it's going to stop, to itself, right? And it's that very recursive nature, and it's fascinating. We'll talk about it more.
So keep in mind that in 2 lectures from now, I think, we're going to really teach you what Gödel's incompleteness is. So just wait for it. Like, it's coming. So I'm going to show you 2 more examples of cellular automata, and then I'll be done. One of them is voting patterns, voting rules. That's what it's called. And what it is, basically, think of people who talk to their neighbors, and their opinion about, which political party is the best, is slowly influenced over time by those people around him. So think of these are like shades of gray, right? Like this person is sort of in the middle. This person's like really Republican or something, and this person is really Democratic. Let's just consider this. So what the rule is for this in the game of life, it was binary. That means there were only 2 states, on or off, alive or dead. But in this situation, there are an infinite number of states. It's a real number between -1 and 1. So what happens is this person has a number, say it's 0.5, and every iteration, he takes stock of the people around him and adds to his number the sum of his surroundings multiplied by some small number. So he's only influenced a little bit, but he's influenced by surroundings. And so what we get is called coarsening. It's a coarsening effect. So the simulation that I'm about to show you starts off with complete noise. It's completely random. Each cell is assigned a value between -1 and 1 randomly. And then we're going to apply this rule and just watch it. It's going to be beautiful. Isn't that awesome? So it's going to keep evolving. And the end state will either be all black, all white, or half black and half white divided somewhere. So, and it's just this very simple rule of summing the cells around you and adding to your state a very low-weighted portion of their opinion. So we get this complex behavior. Like, who would have thought, right? It's really cool. So I'll just go through the code quickly about this one. The structure is pretty much the same as the other ones. These doubly nested for loops going through each individual cell. My is the cell we're at, neighboring cells, blah, blah, blah. So this time, the cell's value is not 0 or 1, but it's a real number. So we sum the neighborhood. So and this line sums up the rule right here, all of it. It says, my next value is my value, my current value, plus the neighborhood sum, the opinion of the neighborhood, times 0.005. Yeah?
If you multiply by a lower number, does that mean it's just going to take like less time to get to the same state?
Yes. So we can actually, this is the beauty of having a live program. So this number, 0.005, determines the speed at which the system evolves. So if we make it 0.05 and run it, you'll notice it'll go a lot faster. It goes really fast, right? It's the same thing, just actually 10 times as fast, because it was 0.05 instead of 0.005. So we can go 10 times slower if we make it 0.0005. Let's make it 0.001, and it's going to go really slow. But that's the essence of the system, just be influenced a little bit by our neighbor. So it's just going really slow now. But it is still going. And interesting fact, cellular automata similar to this one are used a lot to do image processing and graphics, to do like blurring, for example, is a cellular automata applied to the pixels of your picture.
And I'd like to hop in there if you don't mind, Kern.
Yeah, go ahead.
But this is kind of and this relates to a project that Kern and I did with the New England Complex Systems Institute. And this is kind of an example of what we call the universality class of phenomena. But the interesting thing is that this same rule, or this same behavior, is actually what governs gas droplet condensation. So if you look at like the window of your car, and you initially just kind of have misting down on the surface of your window, what each water particle does is, because it wants to fundamentally lower its energy, it wants to take kind of the path of least action. And based on surface tension and the way that essentially the interaction between these water molecules works, is that water molecules like to be next to each other, right? Because it takes less energy to group together than it does for a bunch of water molecules to exist by themselves. And I think it's interesting that the same rules and behavior, which simple things like water droplets on a sheet of glass behave, it's the same way that people behave. Fundamentally, it takes more work if you're just a hunter-gatherer by yourself than to come together in a society and grow collective farms and have someone responsible for this and responsible for that. So in this sense, we really do have a universality class of phenomena. the same laws which govern. And notice this is pure physics when it's in terms of water molecules. I mean, I can actually work out the energy values. Yet, when we're talking about human societies, you don't really have equations. But with cellular automaton, we do. We have equations of how societies interact. And one of the interesting things which the New England Complex Systems Institute is working on is actually prediction of ethnic conflicts and violence. And you can use very simple models like this to predict where if you're talking Gaza Strip, right? We've got Palestinians and Israelis. How do they mix and form together and then segregate each other? And what happens there? And this can all be described using this same kind of very simple graphical rules.
We see complexity because it's there, or we see it because we don't understand the basic laws of the system. And because you see all this stuff, it's almost the same, but we just don't see it. We don't see it.
Okay, so you're asking, like, is it just that we don't see the underlying laws behind society and behind water molecules and things like that? And that really is kind of an idea which Stephen Wolfram, in his book A New Kind of Science, voices, is that the universe really is just a giant cellular automaton. And it's just cranking out these rules, very similar to the game of life.
Yeah, and I can segue very nicely from that into the next thing, which is waves. Now, cellular automata can do waves. And keep in mind that quantum mechanics is basically wave mechanics. Is that right, Justin?
In a lot of ways, yeah.
More or less. And the interaction of particles can sort of be reduced to waves, and standing waves, in a sense. So let's take a look at this program and imagine monkeys typing on a keyboard. What's the probability that a monkey will type this exact configuration of symbols? But it's a lot more likely than a monkey writing like Shakespeare or something. I mean, let's look at, is this the right one? Let's look at this rule. This is really all that we need, this rule right here. So let's look at the rule first, and I'm going to ask you guys to try to predict what's going to happen. So in this situation, each cell has a height, but it also has a velocity, a speed. So you think of it in 3D. The height is the direction this way or that way, and the velocity is the speed at which it's traveling. So look at this rule. And the neighborhood sum is the sum of the heights. The sum of the heights minus my height. So the neighborhood sum is the sum of the differences between my height and the cells around me. So yeah, for each cell in the neighborhood sum plus equals, so that means add this to the neighborhood sum. My height, the cell height for each cell around me minus my height. So if we're the same height, then it's going to be 0. Like if all the cells are the same height, then it's going to be 0. But if there's difference, it's going to be the sum of the differences. And then my velocity is increased by the neighborhood sum divided by 8. So the average of the neighborhood. So what does this mean? What is this going to do? Does anybody tell me?
If everybody around you is like very varied, you may have like a higher one, but if everybody's like the same, you might have like a very low velocity.
Yeah. So yeah, if you're very different than the people around you, then your velocity is going to be higher. Right. So let's run it and see what happens. So it's a wave, right? It's water. So it's fundamentally a wave, and since all particles are waves, it's something to consider that the universe may just be a giant computer. So I added mouse clicks to this so we can actually click on it. So if I click on like the side, hopefully it'll work. What's going on? There we go. Look in the middle. You have things going on and off, on and off, on and off.
It's like a checkerboard.
Yeah, it's like a checkerboard, sort of.
So we don't need all that calculus anymore.
Well, actually, what calculus is doing is approximating exactly this. Or the other way around. This is approximating the calculus. Calculus...
If that's even more detailed, we could like get closer and closer.
So you say...
like more pixels in there.
Right, so he's saying if you have more pixels and more resolution between the possible numbers that you can have, then you're going to approach actual physical reality. Right? Yeah, you're right. But this is the fundamental limitation of computers. They're discrete. So, I mean, there's only a finite number of possible heights for each cell, and there's only a finite number of possible cells that we can have.
The universe itself is discrete in a way.
How's the universe itself discrete?
I mean, time is discrete, space is discrete, and you have like a defined length and everything. So it has to be discrete. It can't be like continuous, because that means within you have like as much matters in the whole universe.
Well, I mean, the way I understand it is the universe is continuous, because take into account, I think, Zeno's paradox, right?
No, but Zeno's paradox, that doesn't make sense. It only makes sense when you recurse and say, okay, when I work from here to there, I'm adding up all these small values of these different things that I add up like in a certain amount of time. So I am moving, because it's not continuous, it's discrete.
Well, what Zeno said is to get from here to here, whoops, I have to first go halfway, and then halfway, halfway.
It bottoms out to like a single value.
But it does not bottom out. It goes on infinitely.
Yeah, but that's on a line. We don't have lines in here.
Well, see, I mean, from here to there, it's a line. And
So fundamentally, the idea is, can we continue dividing matter, like infinitely small?
Maybe you can stop at quarks, atoms, and...
Right. I mean, that's the question, right? Like, are strings the bottom level, right? We're talking in terms of string theory.
but what about space, though?
But
I mean,
Space itself, like,
Space.
doesn't really exist. I mean, it's just like locations, You don't have like a big, you can like imagine like a big Euclidean plane with like all the dots and everything. So
Yeah.
you don't see that. It's just like the way like shown like locations and everything. Like, you can say, okay, to get from like this part over here to that part, I have to go like this much distance, but that distance in the middle is like adding up like little distances, but
Yeah.
you can't get lower than those distances. Those are like the fundamental distances. That's why it's like this
Huh. So you're saying there's a fundamental, the smallest distance possible, or this. Right.
So, but then, here's the question. In our Euclidean plane, which is the universe, and this dot, which is an atom or something, or a particle, when it goes from here to here, does it ever not go through any point in the middle?
There are an infinite number of points that it goes through. The thing itself may not ever be smaller than a certain distance. But see, what we're modeling here is space, not matter. Here, space is defined in terms of these cells, these discrete quantities. But in reality, like there's an infinite number of little, places at which the particle can be. So space is the thing that presents us with this huge divide between simulated things and real things.
Space can be continuous, but the stuff is discrete.
Potentially.
Potentially, yeah.
Potentially, space could also be discrete, and that's kind of the computational view of the universe, which in some ways you're advocating.
So I mean, yeah, if it's so small that we could never detect it, then I mean, it could be the universe could be discrete, right? It could be.
Or maybe space and time, another fundamental thing. Because in quantum mechanics, something can get equals once that's equals can be the same. Something most fundamental than space and time.
So maybe more fundamental than space and time. Yeah, I mean.
That's for the rest of your life to think about.
So I'm finished. We have 10 minutes left. I think I'll hand it back to Justin so he can sort of wrap up.
Yeah, great. I really wanted to pull this into the discussion we were having earlier about kind of what is information, what is what is meaning. And I want to present you actually with a problem that Kern and I tackled with a group of other people during one of these New England Complex Systems Institute intensive week-long seminars that they run in January. And it was the fundamental idea of, like, how do we measure information? How do we measure the content of, say, an image, right? The information content of an image. And why is it that we say that there's more information in an image? And let's just say we're feeding in to a program things like this, but then what's inside of it is might be something like this, right? Now, why do we say that this, in some ways, is more meaningful than just having a bunch of kind of seething dog barf like this? Or, you know, and although I love Jackson Pollock, like, I mean, why do we say that there's, you know, maybe less meaning in these lines than when we had the Sierpinski triangle drawn? And it's really a fundamental problem that's still, you know, people are working on and doing research on. And it involves the way that we can measure information. And one possible measure of information is known as kind of information entropy.
Would it be like kind of about randomness?
Could it be something about randomness? And, well, that's actually fundamentally what a lot of information theory is about, is the probabilities, and to what extent do you expect the outcome, right? And it's interesting that one mathematician named Claude Shannon, back in, I think, the 50s, basically started thinking about this problem and closed a lot of the major problems out in one publication called The Mathematical Theory of Communication. Because he was trying to understand, I mean, what does it mean when we're saying something over the phone and it's going down a transmission line and there's all this noise from the outside world? How do we still extract meaning from those pulses in that electrical cable? And how do we get sounds out of that? And what's the information content there? And if you actually want kind of a rigorous definition of it, if you're talking about kind of one state, we can call h of x, and we kind of take the probability of what we're expecting times the log of that probability. And I can't really derive all this, but and then when you're talking about an ensemble of things, you would just kind of sum over this, and this would become big H. But this is the field of information theory. But the problem is that fundamentally, it's a question of, if I were to take this image and translate it into a bunch of bits, zeros and ones, right? How many zeros and ones would you need for, you know, this versus
Maybe you could, like, in a picture, you may need more for that, but when you abstract from it, you need less.
Exactly. So Latif said, so maybe in a picture like this, you need more, but when you abstract from it, you need less. And this is fundamentally the difference between information entropy and kind of algorithmic entropy. And a really simple problem to think about is, so what takes more, if you were to write a program to give you a number, let's just pick a number essentially at random and say it's 3 billion digits long, and it's you know, 71743, so on, dot, dot, dot. Since this would be a fundamentally random number by definition, the shortest program which I could write to produce this number would be print this number, right? But let's take a different number. What about 3.14159, you know, dot, dot, dot? Anybody here want to show off the number of digits of pi they know? Feel free. I had a friend who was actually failing a geometry class, and on Pi Day, they gave an extra credit point to every digit of pi you could recite. So the hour before class, he remembered 150 digits of pi and immediately brought his grade up to an A. But if you wanted to have a computer spit out pi, it would be stupid to, you know, first calculate it out to 1,000,000 digits and then write print that. But instead, we've got all sorts of different methods for calculating pi. And some of them involve, like, well, you could solve it, using trigonometric formulas, or you could use all these really beautiful series and approach a digit of it when you have, like, the alternating sum of well, for example, right, if you have plus 1/9 plus ... So if you're just taking the sum of 1 over n squared, this is pi squared over 6, right? So in terms of algorithmic information, it's almost something is more meaningful when it takes fewer lines to describe it than in this. And then that's the argument here, is that if you wanted to code this image into zeros and ones, this image would take roughly the same number of zeros and ones as just a bunch of gibberish, right? And that shows kind of a failure of information entropy. But the fact that we can write a program like Curran showed you in just a short few lines that produces this, very quickly, shows that it's algorithmic information. If you were to write a program, is actually much more meaningful. It's not algorithmic entropy, sorry. Complexity. And these are just some rigorous mathematical tools which we're using to think about what meaning is and what information is. And I really hope I've kind of convinced you that a lot of complex phenomenon can come out of very simple things. Yes, Latif?
What if we look at numbers in general, like real numbers?
Yes.
Because when you give a name to a number,
all right, you give a name to a number.
You have so many names to give all numbers. So
yeah.
It's sort of mixing together different symbols and everything. But even if you have an infinite amount of symbols, you can only maybe give each one a bunch of numbers from 1, 2, 3, 4, 5. But what you'll end up with an infinite amount of numbers, but they map to the integers or something. But you're trying to map to the reals, and there's more reals than the integers, so you have numbers that you cannot even say what they are.
So
does that have something to do with the algorithmic complexity? Because some numbers you can't say what they are, therefore they're not computable.
Right. So what you said does have relation to this, but it's actually, you pretty much struck on one of the most fundamental theorems and paradoxes in the past 30 or 40 years. And I can give you some more information on it, but it's called the Lowenheim-Skolem theorem, and it's the idea that, and it's really an idea on logic, and fundamentally, the paradox which you just said shows how, if we really want a theory of meaning, if we want to be able to point out every real number, but we can only do so in a finite way, how do we know that we actually mean every real number, right? Even though we can do it only in a countable way, right? Sorry, so Latif was asking about when you're specifying real numbers, right? So let's take the continuous line from 0 to 1. I know Latif doesn't think this line's continuous, but it is. We only have a certain number of well, here, I'll take it to 2 so I can specify, here's 1. So for example, the square root of 2. 1.41 ... irrational. Infinite digits, does not repeat, so there's no real short way, but we only have a finite number of symbols, a countable number of symbols, in fact, using integers to name this number. So how can we ever say square root of 2 when we only ever have a countable number of integers to start spelling it out? All we can ever do is approximate the square root of 2. I could give you square root of 2 out up to a billion digits, and I still wouldn't be giving you square root of 2, right? But it's kind of I suppose, but then that relates to a really fundamental paradox, which I can't really talk about because it's just kind of way out over the top. But suppose you had something like the way we name, the way we name square root of 2 using mathematics is as whatever x satisfies this equation. And this is really the best we can do, right? But, the idea that you're striking upon, it really is a fundamental one, and it shouldn't be trifled with. But are there any more questions? Because I think I'm running desperately over time. And I'm encouraging you guys to think of these problems. Yes?
I'm sort of thinking when you have like a Euclidean space, it's all continuous and everything.
Right.
Could you like think of consciousness in a similar way? To us it looks continuous, but is it really continuous?
So is consciousness continuous?
Yeah.
Right? So that's a good question, because to what extent do we reduce consciousness just to discrete firings of neurons, right?
As opposed to like the subjective feeling that it feels continuous, but just because it feels like something does not mean it is that something.
So that's actually a very good idea, because he said, so just like consciousness, we feel like it's continuous, but suppose it's not really continuous. One thing to think about is that I think the refresh rate on our eyes is something like 200 frames per second. And that's really why we think things are continuous, but like when we start whirling our hand really fast in front of us, we only see it at certain bits, right? But it's kind of from the continuity of our experience, the fact that it happens so fast that we actually say that we approximate, saying that it took all the positions in between. So it's kind of lazy. Yeah, well, it's the best we can do, right?
It's not good enough.
It's not good enough. All right, fair enough. All right, so I encourage you guys, it might make the typographical number theory chapter make more sense if you glance over the propositional calculus. But really focus on the typographical number theory chapter, and then start processing that handout for chapter 10 that I gave you. And hopefully in about 2 lectures time or so, we can make sense more of what Gödel's achievements were and maybe try to connect a lot of these ideas. But excellent class, guys. I really think this was good. Thank you.